Okay, well, let's go ahead and give it a try. Welcome, everyone. I'll start off by asking if people have any questions to begin with. Comments or contributions. Oh, there's a cute picture. All right. See a number of cute pictures showing up here. Well, thanks everybody for being on board yesterday for Liz's two critically important lectures on genetics. That's a really big deal, and we could and probably should devote a lot more time to it than we do. Um, but there's a lot of competition for topics. I suppose eventually, in terms of sort of curriculum development stuff, there'll probably be an entire course on pharmacogenetics that will be a part of the mainstream curricular offerings for the PharmD program. Okay, well, current event-wise, the very timely arrival of the latest edition of Smithsonian, and there's a ton of stuff in here, a ton of scientific stuff, many pieces which have some direct relevance to what we're doing in the pharmacology course. There's so much in here that I think I might use it again even next week. But one fairly short article that caught my attention with respect to its congruence to our particular interest is entitled "Breathing Easy: How a Brilliant Quip Led to an Asthma Treatment That Helps Millions Every Minute." So there's some really interesting facts and figures in here, and it will relate directly to the course in a few weeks when Kevin Roberts will be with us in a entire lecture that's devoted to asthma, and also a little bit in my lecturing about the autonomic nervous system, because one of the factors in asthma has to do directly with homeostatic matters that are relevant to autonomics, physiology, pathophysiology, and pharmacology. Kevin goes into a lot of other things, of course, also in his lecture, but there's a very direct connection to autonomics, and I'll comment a little bit on that as we take a quick look at this. So it starts off in the mid 1950s, which I think perhaps we've already seen was a very fertile time in the history of pharmacology. A lot of developments were occurring post World War II, and setting the stage for revolutionary events that were upcoming as technology developed in the 1960s and 70s. So a number of these stories actually do start in about the mid 1950s. So this article, which I'm sure you could probably find, many people don't do that much with actual sort of paper journals and magazines anymore, doing everything on the web. Smithsonian has a really nice website, and I suspect you could probably pick up each issue on the website. Also, for anybody that does watch television, there's a Smithsonian channel, and it's maybe not quite the impact that the National Geographic channel has, but it's pretty good. So this article starts off: in April 1955, 13-year-old Susie Mason asked her father, a pharmacologist, George Mason, whether there wasn't an easier way to treat her asthma. Like so many other people with the affliction, she'd been using an awkward squeeze bulb nebulizer, and she wondered why her medicine wasn't available in a spray can. Like they do hairspray, she said. Though nebulizers of that era were more effective than the medicated, listen to this piece of terminology, asthma cigarettes previously in vogue, Susie's father too had been frustrated by the cumbersome process of refrigerating the vials of medicine and loading them into the delicate contraption. Mason, the father, was no stranger to innovation. As an Air Force lieutenant during World War II, he planned the first system for aerial rescue behind enemy lines and earned a Legion of Merit award for perfecting the anti-gravity suit. At the Boston University School of Medicine after the war, he developed Verilloid, the first widely distributed prescription drug to treat hypertension successfully. Um, along with some other things that were introduced there in about the mid 1950s that we'll talk about a little bit more when we get into autonomic drugs in another week or so. If you remember, we talked a little bit about reserpine the other day, and reserpine is another example of the mid 1950s introduction for both hypertension as well as psychoses. The article goes on, now as president of Riker Laboratories in Los Angeles, Mason was in the rare position to investigate his daughter's question. He assigned Riker's lead chemist, Irving Borush, to experiment with the possibility of a pressurized device. At the time, Riker was owned by Rexall Drugs, which did indeed manufacture hairspray. Borrowing expertise on propellants and aerosols from the cosmetics technicians down the hall, and using a recently patented metering valve capable of delivering precise amounts of atomized liquid, Borush created the first metered dose inhaler in just 2 months. By March 1956, the FDA had approved 2 new aerosol drugs for asthma, as well as the device for delivering them. It was a game changer, says Stephen Stein, a scientist at Kendeva Drug Discovery, a descendant of Riker Labs, and co-author of a recent history of therapeutic aerosols. Today, here's some interesting numbers. Today, sales of pharmaceutical inhalers exceed $36 billion globally each year, and the device has puffed its way into medical history, improving the lives of millions. More than 2,000 people around the world use one of these devices every second. Absolutely incredible stuff, and gives a little example of a advertisement about this inhaler, and mentions the active drug ingredient isoproterenol, which I think many of you know is sort of the classic beta agonist, and certainly as we turn into autonomic drugs here in another week or 10 days, isoproterenol and its offshoots. And it also mentions epinephrine here, of course, which is one of the real classic physiological and pharmacological substances. So interesting stuff. See if anybody has any thoughts or questions on that.
I have to ask, what is an asthma cigarette?
I don't really know. That's the first time I've heard that terminology, and I assume it's not referring to any sort of tobacco sort of thing, but just sort of the physical nature of some sort of presentation in which you were allowed to then absorb the volatilized drug substance from the from the so-called cigarette. I don't know. That's the first time I have ever heard that terminology, and I'll look it up and let us know. And that's a good question.
I'm assuming and they're talking about like an aero chamber that then helps a child absorb the drug rather than having to worry about like a in and out puff. The aero chamber kind of looks like them sucking on a cigarette, but like a larger size.
Oh, okay. Thanks. Well, that's helpful. Maybe we can come up with a net-based photograph of so-called cigarette to buttress what you just said there. Thank you.
I was just looking it up, and they look a lot like cigarettes in the pictures.
Wow, that's scary.
I think back a long time ago, they actually used to use cigarettes as a treatment for asthma. So I don't,
So maybe it was actually a tobacco-containing
it might be, yeah.
substance. Well, that's possible, as we'll talk about it a little bit later in the course, and many of you already know. Um, cigarette smoke is a very complex matter, and there are just many different compounds, many of which are adverse, but some of which aren't. In that,
Hey Keith, I found one. A formulation, they're called Pages inhalers. They are genuinely medicated cigarettes, so they are cigarettes
well,
with stramonium leaves, chestnut leaves, tea leaves, gum benzoin or benzion, and cola nuts. So that's one formulation that was from Pages inhalers, which is it looks like new package adopted in 1956. So 19.
yeah, that's right on time-wise. And wow, what an amazing combination of substances there. Well, I would have lost that bet. Thanks everybody for looking. Who knows what you're going to run into in pharmacology each day, right? Somebody asked you what you did in pharmacology today, said, well, we talked about asthma cigarettes. That ought to get a blink or two. Okay. Well, we're going to spend some more time with this quick look at pharmacokinetics today. And perhaps if we have enough time, a little bit, not much, but a little bit more detailed look at one of the components of pharmacokinetics, that being metabolism. But if we don't quite get all of that up to date, we'll just continue with it as we move on next week. So this quick journey through pharmacokinetics is not meant to be one of expertise, but rather one of awareness. It's sort of like you do music appreciation, this sort of pharmacokinetic appreciation, and as we've talked about, something needed to lay the groundwork for pharmacodynamics, which is the main thrust of our course. And so this first slide which we've already looked at, was just one, which is looking at some of the major interactions of pharmacokinetic parameters. And likewise with slide 2 here, very creatively labeled pharmacokinetics. So the next slide, dealing with membranes, of course, has some relevance to the asthma cigarette, in that we would consider that to be a formulation for delivery of drug substances, now just become a historical piece of information more than anything. We talked a little bit about characteristics of drug substances in terms of size and lipid solubility, polarity, and so on. And all those are relevant with respect to administration of drug substances and ultimately absorption into the system. Absorption would be a topic relevant to the asthma cigarette in the context of delivering one or more drug substances to the lung mucosa. So, all types of administration it involve absorption to some degree, except for, of course, like intravenous administration, in which you circumvent the absorption side of it and directly deliver a drug to the blood. But even then, those parameters such as size and lipid solubility, polarity, and so on are important in terms of the ultimate distribution from that absorption site. And we'll talk more about distribution here in just a few minutes. Of course, the importance of these physical chemical parameters has much to do with the fact that as drugs are moving throughout the system and from one compartment to another, they're moving across biological membranes. So the characteristics of drugs which relate to biological membranes are right on in terms of these movement processes for drug substances. In terms of distribution, two really important sub areas of distribution for our purposes are listed in the latter part of this slide: the blood-brain barrier and the placental barrier. Now, the use of terminology barrier is somewhat misleading. I think it's terminology that was introduced decades ago, and once those pieces of terminology become entrenched in the way of thought, they don't really go away. So I don't think we're going to see much in terms of changes of this terminology. But I sort of prefer the terminology of resistor, the blood-brain resistor and the placental resistor, because it perhaps suggests that both of these systems are really somewhat less than barriers. Now, the blood-brain barrier is pretty much a barrier to very, very highly polarized and large molecules, which really don't make much entry into the brain at all. But other substances which maybe have some challenges of getting into the brain ultimately make it in there, but have to circumvent the resistance characteristics of the blood-brain barrier itself. And we'll talk as we get into CNS pharmacology. We'll talk more about the nature of the blood-brain barrier. Some of it is pure physicality, such as involvement of glial cells and their membranes in providing an additional sort of one or more membranous surfaces that a drug has to go through to get into the brain. But there are also metabolic components of the blood-brain barrier. So a variety of characteristics come into play in terms of this highly evolved characteristic of the vasculature that leads to the nervous system. Now, you can probably appreciate that one of the major reasons, in my mind anyway, from an evolutionary standpoint, why the blood-brain barrier isn't a real barrier is that many of the nutrient substances that are required for our successful existence must also, of course, get into the brain. And these substances have similar physical chemical characteristics to toxins and drugs. So if you made a firmer barrier, you would in more drug and toxic substances from the brain, but you would also exclude important nutrient substances from getting in there. So it's a sort of a challenge physiologically to balance those things off in an evolutionary development standpoint of having something that does offer some resistance to substances going in, but not too much. Now, the placental barrier is even less of a barrier. It's pretty leaky, and it would be fantastic if it was a stronger barrier. In that, of course, we all know about teratogens, which are fetal malformers, and in a better barrier would probably exclude more teratogenic substances. But then again, on the other hand, that firmer placental barrier would also once again restrict other important substances from getting inside. Um, so it's a contrast that goes on there in terms of risk benefit analysis. And we'll certainly talk about breaches, if you will, of the blood-brain barrier as we go along and take a look at a number of different drug topics. I think if you sort of do a calculation about how much of a barrier the placental barrier is, it turns out that most, not all, but most substances make it across the placenta. And we have to be on guard very much for the effects that these substances have on the developing fetus. Very, very important topic. So this is just a little reminder about membranes, and I'm going to just flick right past it. Really, you're all quite familiar with the nature of cellular membranes from your studies in biochemistry and physiology and so on. So I'm sure you remember most of those things, and if not, it might be worth a few minutes of review in biochem and physiology to remember key characteristics of the plasma membrane and other types of membranes. Just a little note there, an important one from a pharmacological standpoint is that a small molecule like alcohol and a molecule would sort of sits at that relationship between polarity and non-polarity. It's sort of in both those worlds. Has a little problem in crossing membranous barriers, including the ones that we just talked about. And so administration of a small lipid end polar-like molecule such as alcohol results in near systemic distribution and access to really most, if not all, of the compartments available throughout the broader system. So we'll certainly come back to that when we study alcohol in a few weeks or a month or two. So really critical stuff there. And of course, alcohol is perhaps the most classic teratogen around. And so obviously, when alcohol is administered in an individual, if there's a pregnancy, the alcohol achieves nearly the same concentration in the fetal circulation as it does in the maternal circulation. And the next slide, entitled Routes of Administration, is just a maybe a little bit complex but nice pictorial representation of various types of administration, including injection types and inhalation, which of course doesn't necessarily always involve burning of a substance such as with tobacco or asthma cigarette, but anything that will volatilize substances will ultimately allow for inhalation administration. And inhalation is a very thorough and complete, efficient, type of administration. But if you can achieve it without burning, it's fantastic, because burning creates such complex mixtures of substances. So, as I promise, I toss some things in along the way, which are there more as aspects of their beauty and and perhaps tension relief like this one. This is such a cool picture, I think. And if anybody is feeling a little bit tense later in the day, maybe you come back to this one and it'll lighten the load a little bit for you. But put Papaver somniferum in because it's a beautiful thing. The opium poppies are really absolutely stunningly beautiful flowers. And then the pharmacological contents, of course, are incredibly important in terms of both pharmacology and toxicology. And it's interesting to note that the various components of opium, as well as the synthetics that have been developed in about the last 100 years, following the recognition of those substances, some of those substances uh, in the natural product, opium poppy, that literally all the various routes of administration, from oral to the various injection routes to inhalation to topical, are possible with respect to the naturally occurring opioids as well as their synthetic derivatives. So even though that's not really why I put this pretty picture in here, we can relate it to our current topic rather readily. So, mostly we've been talking about passive diffusion across cellular membranes, the movement of alcohol, for example, across plasma membranes is, pretty much a passive diffusion process. And really the characteristics of alcohol and related types of molecules are such that you don't really need a specialized way to get the substances across the membrane if they're going to cross at all. But there are, of course, various types of specialized channels and transporters which are available to assist the movement of some substances across biological membranes. And facilitated transport is an example that we'll talk about a little bit more in a few days. But there are various sorts of labels that are put on these various channels and transporters. And diffusion through gated channels, is an example of assisted transport, but not really one that requires an energetic, a specialized energetic component. Whereas active transport requires energy for that movement at all. So there are some differences in themes here as you go from sort of the more generalized passive diffusion to the more specialized active transport. And this is just a little cartoon that's related to that previous topic. And I'm not going to spend a lot of time with this. For those of you, again, which is most of you in the class, but not everyone that will be taking that you are taking the pharmacokinetics course, you will talk about in some detail the differences between these various passive and active modes of transportation across membranes. A really big deal in pharmacokinetics has to do with the relationship between the pKa of a drug and the pH that is exposed to in whatever compartment we're talking about in the physiological system. And of course, ionized substances are, have a harder time getting across biological membranes than non-ionized substances are concerned. So in the pharmacokinetics course, a great deal of attention is paid to various processes of ionization and non-ionization. And right now, I'm just going to mention it as one of our familiarity with the idea that the non-ionized form is typically the most likely form to be moving across the biological membrane to any extent or degree. And indeed, as we get into each of our specialized drug topics, such as, first of all, autonomic drugs here coming up later next week or the following week, we'll take a look at those situations where various autonomically related drugs either find themselves in the non-ionized or the ionized state, and the impact that ultimately has on concentration at drug site of action and the pharmacodynamics of autonomic drugs. This one I'm going to just skip right by. It's the sort of pictorial representation of absorption that you'll see a lot in pharmacokinetics, and no surprise, I'm sure, to individuals that in a time-based process like this, IV administration results in an earlier and a sharper peak than oral administration delivers. But the complexities of this process are beyond our interests right now as far as pharmacology is concerned. An important definition, and one of the things that you can think about in terms of examination matters when we get to that here in another few weeks, is that many of the things that can be tested upon in this particular segment have to do with definitions. And so anytime you run into something like the slide that we're looking at now entitled drug bioavailability, then that definition is likely to find its way into one or more examination questions. And of course, a fairly straightforward definition in this case, the extent to which a drug reaches its site of action. And once again, that concentration at that site of action is what we're so interested in terms of dose response in pharmacodynamics. So obviously, drug bioavailability is an absolutely essential precursor to the ultimate pharmacodynamic characteristics of drugs. So we've already been talking about drug distribution to some degree. It's just really inevitable as you start thinking about the administration and absorption of drug substances, is ultimately thinking about their distribution within the system. And some drugs have rather limited distribution, which is sometimes a problem in the sense that, for example, if you have an infection in the brain and you're having to deal with the resistance characteristics of the blood-brain barrier, then that restriction on distribution can be a limitation to the ultimate therapeutic goals that you have for an antibiotic substance. But on the other hand, in situations where there's little, if any, resistance to movement of drugs throughout the system, such as with alcohol, it means systemic distribution and potential problems associated with that systemic distribution in one organ system or another throughout the broader based body. So obviously, distribution refers to the reversible transfer of drugs from one location to another within the body. Sometimes these transfers almost seem irreversible, but they will be reversible as long as you wait long enough. So in certain situations where there's quite a bit of affinity for a particular drug substance, for a particular subsystem, such as those drugs which partition into fat stores readily, it just means that the drug is going to be in that location for a long period of time. And if you wait weeks or months, ultimately it will partition back out into the circulation and eventually be eliminated from the body. But clearly, the pattern and distribution reflects the physical chemical nature of the drug and the ease with which it penetrates drug different membranes, as we have already talked about earlier this hour. So this is just taking a little bit more detailed look at both rates and extent of distribution throughout the system. Some of these characteristics that we've already talked about, but one that I would like to point out, which is so important, of course, is that drug substances, speaking generally, have affinity for various sorts of proteins. The greatest affinities, of course, are with discrete receptors, but there's a lot of protein binding which is not receptor based, which is still nevertheless important as far as distribution or lack thereof in the realm of pharmacokinetics. Our blood is just filled with various sorts of proteins, and particularly plasma binding is critical. And so one of the important characteristics for isolation of drugs in the system has to do with protein binding. Did I hear a question coming up there? Maybe not. I make up things sometimes. So there can be sort of discrete types of protein binding in the plasma, or more generalized binding to things like albumin. And if there's a very tight or high extent binding of drug substances in the blood, then that plasma, for example, becomes an important reservoir for drug distribution in the system. But of course, there are many proteins with important binding characteristics outside plasma in various sorts of tissues, and other important biological molecules, which are important as far as distribution is concerned. Fat being one of the most important of them, and fat cells in fat tissue comprise a critical source of drug substances once they've partitioned into fat. And if we take well-known examples such as cannabis and steroids, the partitioning of those substances in and out of fat is a very important dynamic phenomenon as far as the distribution of those substances is concerned. Now, volume of distribution, I mentioned it here almost with reluctance because it's a very complicated topic, and it's one in which there's tremendous potential for me to butcher the topic and confuse you more than enlighten you. But again, for those of you in the pharmacokinetics course, volume of distribution is and will be a really important parameter for detailed examination on your parts. Notice the word apparent volume of distribution, and that's an important modification of that word volume of distribution, because the apparent volume of distribution is probably different than what you would imagine the actual volume of distribution to be. And in actual volume of distribution, you would see volume values, which would be no larger than the total volume of the body. But when you have a chance, even in our pharmacology books, there are some interesting tables. It's in the back of the Goodman and Gilman book. You'll see some tables that relate to volume of distribution and other important pharmacokinetic characteristics of the drugs which are most important in our discussions. If you have a few minutes sometime and you're just looking for something wild to do, take a look at some of those volumes of distribution, and you'll see values there, some of which are extraordinary. You'd think, wow, that must be administered to an elephant, or others which are so small it looks like it must be a fruit fly, that, in which you're talking about the volume of distribution. In other words, the the uh, the, the way volume of distribution is measured does not necessarily give you a realistic volume physiologically. Nevertheless, volume of distribution is still an important pharmacokinetic characteristic, and that's why you spend so much time with it in the pharmacokinetic course. So if you get specialized distribution, like a whole bunch of plasma binding or partitioning in fat, or on the other hand, hardly any uh, 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 characteristics like that, then you're going to get these wild, really too large or really too small volumes of distribution. But hopefully not having put too much misunderstanding into that. Nevertheless, getting the point across that volume of distribution is an important parameter. Indeed, is an abstract process, but it nevertheless is informational in terms of how the drug is distributed in the body. And something with a really huge volume of distribution is clearly more widely distributed than something with small. And so, in terms of the actual initial administration of a loading dose of drug substances, volume of distribution is important in that particular calculation. Again, which will be explained in some detail to you in the pharmacokinetics course. For those of you who aren't taking the pharmacokinetics course, if you need better explanation of some of these topics, we'll find a way to do that for you. Let me know about that. The actual sort of mathematical formulation of volume of distribution, as you can see, is dependent upon concentration in plasma, as well as the amount of drug that's actually calculated in the body. And there could be other ways to measure volume of distribution, but this is sort of the classic pharmaceutical sciences way of measuring volume of distribution. And we just gave some examples here, and those are pretty interesting in terms of their numbers. So for amitriptyline, for example, which is an important antidepressant drug, as many of you know, volume of distribution is about 1,000 liters. That's a big individual. So, of course, as we talked about initially in the life history of a drug substance, as the drug enters the system to begin its process through the various pharmacokinetic factors, ultimately it's going to be a quote unquote completely eliminated or excreted from the system, with that caveat that I already talked about, how in terms of first order processes, you approach that limit very, very slowly. But for pharmacological practical purposes, what goes in comes out. And the important routes of elimination are especially the kidney and the fecal contents. But drugs can be eliminated via any biological fluid. And so things like sweat, saliva, and in the specialized case of milk are other important routes of elimination. But by far, from a quantifiable standpoint, the urine and the feces are the most important routes of elimination. So again, as I think we've already talked about a little bit, the characteristics, the physical-chemical characteristics of drugs, allowing them to get into the system and be absorbed and moved around the system, are not the characteristics which are amenable in many cases for ultimate elimination of the drugs. So one of the characteristics that the system has to assist ultimate elimination of drugs and toxin has to do with metabolism, which will see some definitional aspects over the next couple of slides. And so there are a variety of enzymatic systems available for ultimate chemical transformation of drug substances. One of the most prominent of which is seen sort of mid-slide there, the microsomal enzymes, which we'll talk about in a little bit more detail as we go along. So here's sort of a definitional slide for your interest: metabolism, drugs, and other xenobiotics, meaning things coming into the system from the outside, moving from initially more hydrophobic to eventually more hydrophilic metabolites is essential for the elimination from the body and termination of their biological activity. Now, one little thing to mention here is that sometimes metabolism is directly equated with lowering the biological activity of a drug substance. That's not necessarily the case. Metabolism may lower the biological activity, but one thing for sure it does is allow for ultimate termination of the biological activity by getting it out of the system. So metabolism can increase, decrease, or not affect biological activity per se, depending on the drug substance in question. So here's just this idea that metabolism is biotransformation. And I think the various characteristics that we've talked about on this slide, we've already discussed. So we'll stop here in just a minute, but before we do that, let me just mention that a couple of pieces of important terminology as far as metabolism is concerned has to do with phase 1 and phase 2 metabolic reactions. And probably the place for us to spend our time next would be to give some examples of what do we mean by phase 1 and phase 2 metabolism or biotransformations. And basically, in thinking about metabolism as either being catabolic or anabolic, phase 1 reactions are basically catabolic or breakdown reactions, and phase 2 reactions are basically anabolic or build-up reactions. But both of those, whether phase 1 or phase 2, essentially lead to greater polarity and ultimate greater ability to eliminate the drug substance from the system. So this is about where we'll start next time. A little bit hard to believe, everybody. We've already gone through 2 weeks of class. Time just marches on, and we'll wrap up our review of pharmacokinetics as we begin next Tuesday at 1, and then move into pharmacodynamics before we then move on to discrete drug groups like the autonomic drugs. So that's where we're heading. Be safe, everybody. Have a great weekend, and we'll see you next Tuesday at 1.
Have a good week.
Thanks, everybody. Take care. Best wishes to all of you.
Thank you.
Mm-hmm.
Thank you.
You're welcome.
Thanks, Keith.
You're welcome, and thanks also to all of you